So here we have a rational function, and we're going to find the vertical and horizontal asymptotes, and we're going to find the x and y intercepts. This is a topic in college algebra as well. So this video can be seen by Math 1430 and Math 1220. Okay, and this will help us if we're asked to graph a function. It's always nice to find asymptotes for the rational function and intercepts, because that will help us get the graph. Okay, so I'm going to do the asymptotes first. So let's do the vertical asymptote. To find the vertical asymptote, this fraction is simplified. So I can't factor the numerator, so I'm just going to write 2x squared minus 9. The denominator I can factor as, let's see, since it multiplies to a positive, the signs are the same. We're going to make them both minus. So I'm going to write minus 2 minus 3. So to find the vertical asymptote, you set the denominator of your simplified function, which this is simplified, no canceling can be done. So set the denominator equal to 0. And then we just use the zero factor rule. When does my first factor equal 0? When does x minus 2 equal 0? Add 2 to each side, you get x equals 2. And then when does x minus 3 equal 0? When x equals 3. So we have two vertical asymptotes. Remember, vertical asymptotes are lines, so don't just write 2. You must write x equals 2, x equals 3. And by the way, this is going to imply 3 branches on our graph. If you have two vertical asymptotes, you're going to have 3 branches. And I'll talk more about that later if I remember.
I'll tell you right now, the number of branches is one more than the number of vertical asymptotes. We only have 2 vertical asymptotes. So what's 2 plus 1? 3. That's a good thing to know for graphing anyway.
If we only had one vertical asymptote, x equals 2 say, then we would have 2 branches. So by branches, I'm just going to make something up here. This would be considered a branch. And then maybe we would have something like, let me think for a second. Maybe, so we have 2 vertical asymptotes here. I'm just making something up. This has nothing. Maybe this would be a branch, and then maybe, let's see. So that's what I mean by branches, pieces of the graph. This is considered one graph. It's got 3 branches. So notice I just randomly wrote 2 vertical asymptotes with these dotted lines. This looks like x equals 0 and x equals 2. So this has nothing to do with this problem. But the point is, if you have 2 vertical asymptotes, you're going to have 3 branches for this one graph. Okay, so that's enough with that. All right, so we found our vertical asymptotes. Let's find the horizontal asymptote. To find the horizontal asymptote, I know it always begins with y equals. Don't write a number. It's got to be a line. It's a horizontal line, which means y equals number.
Spells the word hey.
Yes, so if you see the word hey, that's a good sign. You're doing things good. Okay, so let's compare it. So I'm going to look at, it's better to look at this original function. Y is the same thing as f of x, by the way. So look at the degree of the numerator. The highest exponent is the degree of the numerator, which is 2. What's the highest exponent in the denominator? 2 as well. Since the exponents agree with each other, and whenever the degree of the numerator equals the degree of the denominator, then the horizontal asymptote is y equals the ratio of the leading coefficients. Notice it should always be in standard form. Exponents go from high to low. So this numerator's in standard form, denominator's in standard form. So what's the ratio or fraction of leading coefficients? It's going to be 2 over the implied 1. 2 over 1 is just 2. So there it is. We're done with the horizontal asymptote. Y equals 2.
So let's speak for a moment about how do you find the horizontal asymptote of a rational function? First step, compare the degree of the numerator to the degree of the denominator. If they're the same degree, divide leading coefficients, which is what we did here. What would happen if the degree of the denominator were bigger than the degree of the numerator? Then it's always y equals 0.
Okay, now let's go to the intercepts. The y-intercept is usually easier to find, so I'll do that one first. To find the y-intercept, here's the rule. Let x equal 0 and then solve for y. So it doesn't matter which one I look at here. I think this one's easier. To find the y-intercept, wherever you see an x, you let it equal 0. So if x is 0, this first term goes away. So I'm going to write y equals, the numerator is just going to be negative 9 over, when x is 0, the first two terms go away, but now we have 6. 0 minus 0 plus 6 is 6. And that reduces, 3 goes into each one of these, so negative 3 halves. I like to write it as an ordered pair, so let's write it as an ordered pair. To find the y-intercept, x is always 0, and y in this case is a negative 3 halves. Okay, and now to find the x-intercept, let me write that over here. Here's the rule. Let y equal 0 and then solve for x. So I'm going to let y equal 0. So I'm going to write 0 equals this fraction. 0 equals 2x squared minus 9 over x squared minus 5x plus 6. Clear the fraction now. So multiply both sides by x squared minus 5x plus 6. That's the LCD. So if I multiply both sides by x squared minus 5x plus 6, what's 0 times that? Still 0. And for the right-hand side, the denominator is going to cancel. So it's just going to be 0 equals the numerator.
Or you could have set cross products equal to each other. You could have written 0 over 1.
Yeah, over 1, and then set the cross products equal.
And you get the same thing.
Same thing. Okay, let's add 9 to each side. So I'm going to get 9 equals 2x squared, which is the same thing as saying 2x squared equals 9. And now divide each side by 2. I'll continue over here. Dividing each side by 2, I get x squared equals 9 halves. So take the square root of each side to get x equals plus or minus. The square root of 9 halves, that's the same as saying the square root of 9 over the square root of 2. And that's going to be plus or minus 3 over the square root of 2. Let's rationalize the denominator. So I'm going to go square root of 2 over square root of 2.
Multiply this fraction by another name for 1. Why not choose that denominator?
This is like a 1 here. So it's going to be plus or minus 3 square root of 2 when I multiply the numerators over 2. I'm going to write them as ordered pairs now. So when I look at the positive answer, I get x is 3 square root of 2 over 2 comma 0. And then my other x-intercept is negative 3 square root of 2 over 2 comma 0. And then if I want to graph this function, which I'm not going to do, but I'm just going to start you off anyway, here's how this stuff helps us. The horizontal axis, the vertical axis is always y, the horizontal axis is x. So y equals 2 is the horizontal asymptote, so go up 2 on the y-axis, and then draw a dotted line, because these asymptotes are just guidelines.
They're not part of the graph, really. They're just guidelines.
Okay, and now the vertical asymptote is x equals 2. So draw a dotted line here, and it's nice to label your asymptotes.
Remember, your graph can never touch or cross a vertical asymptote. And for a horizontal asymptote, sometimes the graph will touch or cross a horizontal asymptote for small values of x.
My other vertical asymptote is x equals 3. We have a y-intercept of negative 3 halves. So on the y-axis, go down 1.5. There's negative 3 halves, we'll say. There's 1 and there's 2. I don't know. This should be right in the middle, actually. Okay, so there's my y-intercept. I'll label it 0, negative 3 halves. And then you would need a calculator to see what this is. The square root of 2 is roughly 1.4. 3 times 1.4 is roughly 4. 4 divided by... So this is close to 2. So it's a little, maybe, let's say it's a little higher than 2, I think. I'm not sure. So this would be an x-intercept, roughly. And then the other x-intercept is in the opposite direction. So it's going to be equidistant on the left side of the x-axis. And then the graph must go through. So I'm just going to take a guess here. I could plot more points to be more accurate. But I have a feeling it's going to look something like this.
Notice how my brother's using those asymptotes as a good guideline to draw these branches. This is actually going down. It's never going to cross or touch that.
Yeah, it goes down. It'll never touch x equals 2, that vertical asymptote. And then this asymptote, oh man, who knows what this is going to look like. It could actually touch this horizontal asymptote, but I don't want to make this video too long. So,
but you could just pick something on either side of the vertical asymptotes. If you let x equal 2.5, for instance, that would give you an idea of where that y will be.
Let's just guess. Pretend if x is 2.5, y is up here. So probably it might look something like this, but not touching. And then over here, where is the third branch going to go? Is it going to go above or below y equals 2? So what I would do is pick a point x equals 4. This is to the right of this vertical asymptote to see where this third branch goes. So if x equals 4, I'm going to just do that right now. If x is 4, 4 squared is 16, 2 times 16 is 32, 32 minus 9 is 23, over, when x is 4, 4 minus 2 is 2, and then 4 minus 3 is 1. 2 times 1 is 2. So 23 halves is 11 and a half. So when x is 4, y is way higher than y equals 2. It's going to be up here somewhere. So now I know that we're going to approach the vertical and approach the horizontal. So there's our 3 branches. And I might be wrong on this branch because I don't want to spend all day on this problem.
But notice this graph does pass the vertical line test because this is a rational function. A rational function.
All functions pass the vertical line test. Okay, good night, everyone.